The lattice structure of the semiconductor materials is crystalline. Let's look at some properties of the crystalline lattice. In week 2, we have already introduced its lattice properties. Crystalline silicon has a cubic diamond structure. A crystalline lattice means that atoms are arranged in a certain pattern, which repeats itself. A crystalline lattice has long-range order and symmetry. However, it does not mean that this pattern is the same in every direction. Or in other words, if we make a large cut through the lattice, the various planes you can make do not look the same. Here we see two planes of two different cuts in a crystalline silicon lattice, which originally consisted out of 3 by 3 by 3 unit cells. We see two important surfaces. The first one is referred to the 100 surface, and the normal of this plane points in the 100 direction. The silicon at the 100 surface always has two back bonds and two other valence electrons pointing to the front. The second surface is the 111 plane. It can be characterized by 3 silicon back bonds and 1 valence electron pointing in the normal to the plane. Why are these directions important? As we have discussed in week 3, we have direct and indirect band gap materials. This can be expressed in the so-called electronic band dispersion diagram. On the vertical axis you have the energy position of the valence and conduction band, and on the horizontal axis the crystal momentum, or in other words the momentum of the charge carriers. To be excited into the conduction band, the charge carriers in an indirect band gap material require a change in energy and in momentum. Here we see the real electronic band structure of the crystalline silicon. The white area reflects the energy levels in the forbidden band gap. The horizontal axis reflects the lattice momentum in various directions. The band gap of silicon is determined by the lowest energy point of the conduction band at X related to the 100 direction and the highest energy value of the valence band at gamma. Now we zoom into the band gap area. The band gap energy is the difference between those two levels and equals 1.12 electron volt, or 1107 nanometers, expressed in wavelengths. This transition is an indirect transition. I repeat again, the charge carriers need energy and momentum transfer to be excited. As you can see, crystalline silicon has a direct transition as well. However, this transition has an energy of 3.4 electron volts, which equals a wavelength of 364 nanometers. This is in the blue spectral part. For an indirect bandgap material, it's less likely that a photon above the bandgap is able to excite the electron into the conduction band in reference to a direct bandgap material. Consequently, the absorption coefficient of crystalline silicon in reference to direct bandgap materials like gallium arsenide and indium phosphide is significantly lower, as we can see in this plot. Crystalline silicon is indicated by the red line, whereas gallium arsenide and indium phosphide is indicated in yellow and green. You can see that in the visible spectrum, crystalline silicon absorbs less than the gallium arsenide and indium phosphide, but below 364 nanometers, it absorbs just as much as gallium arsenide and indium phosphide, because silicon has a direct band-to-band transition here as well. Germanium, indicated by the blue line, is like silicon. It is an indirect bandgap material. It has a bandgap of 0.67 electron volts, which means it already starts to absorb light at wavelengths below 850 nanometers. In the visible part, germanium has some direct transitions as well. Let's consider the design rules for solar cells as introduced in week 3. Let's start with spectral utilization. A band gap of 1.12 electron volts means that in theory we can generate a maximum short circuit current density of 45 milliamps per square centimeters using crystalline silicon. Let's consider the third design rule, light trapping. First, we look at a wavelength around 800 nanometers. Crystalline silicon has an absorption coefficient of 1000 per centimeter. You can simply calculate using Lambert's law that to realize an absorption of 90% of the light intensity at 800 nanometer, it requires an absorption path length of 23 microns. Around a wavelength of 970 nanometers, crystalline silicon has an absorption coefficient of 100 per centimeters, and it requires an absorption path length of 230 microns to absorb 90% of all the light. This is a typical thickness of silicon wafer. This demonstrates that the light trapping techniques become important for crystalline silicon absorber layers above a wavelength of 900 nanometers. Let's consider the last design rule, which is the utilization of the bandgap energy. As discussed in week 3, the bandgap utilization is determined by the recombination losses. As silicon is an indirect bandgap material, only Auger recombination and Shockley-Reed-Hall recombination will determine the open circuit voltage. If we consider Shockley-Reed-Hall, the recombination of charge carriers is related to the electrons trapped at defect states. In view of defects in the bulk of silicon, we can make a general difference between two types of silicon wafers: monocrystalline silicon and multicrystalline silicon, or also called polycrystalline silicon. Monocrystalline silicon, also called single crystalline, is a crystalline solid in which the crystal lattice is continuous, unbroken without grain boundaries over the entire solid up to the edges. In contrast, polycrystalline silicon, often abbreviated with polysilicon, is a material that consists of many small crystalline grains with random orientations. Between the grains, polysilicon has grain boundaries. Here you see two pictures of monocrystalline and multicrystalline wafers. Monocrystalline silicon wafer has one uniform color, whereas in multicrystalline silicon the various grains are clearly visible for the human eye. At the grain boundaries we find lattice mismatches. As a result, many defects reside at the grain boundaries. Consequently, the lifetime of charge carriers in polycrystalline silicon is shorter than for monocrystalline silicon due to the Shockley-Reed-Hall recombination. The more grain boundaries in the material, the shorter the lifetime of the charge carriers. It means that the grain size plays a role as well. In this figure from a paper of Bergman, we see the relation between the open circuit voltage of various solar cells developed over the world based on the multicrystalline wafers. On the horizontal axis, the average grain size of the multicrystalline silicon absorber layer is shown. The larger the grain size, the longer the charge carrier lifetimes, and the larger the bandgap utilization, and the larger the open circuit voltage will be. On the right you see now the open circuit voltages of various solar cells based on monocrystalline silicon wafers. As monocrystalline silicon has no grain boundary, much larger open circuit voltages can be obtained. The question now is, how do we make these types of silicon wafers? How do we make monocrystalline and how do we make multicrystalline wafers? We will discuss that in the next block. We have various types of silicon wafers such as monocrystalline silicon and polycrystalline silicon. In this block I will give an answer to the question, how do we make these various types of silicon? How can we make the silicon material pure? The lowest quality of silicon is the so-called metallurgical silicon. The source material of making metallurgical silicon is quartzite. Quartzite is a rock of pure silicon oxide. In the next animation, the process of making metallurgical silicon out of quartzite is shown. During the production, the silicon is purified by removing the oxide. This happens in a submerged electro arc furnace. The quartz side is moved into the furnace where it is melted. Using an electrode, the quartz side is heated up to a temperature around 1900 degrees Celsius. The molten quartz side is mixed with carbon. Carbon source is a mixture of coal, coke and wood chips. The carbon reacts with the silicon oxide. I won't discuss the details of the reaction, which is rather complex, but the result is that the oxygen is leaving the furnace as carbon monoxide. The molten silicon that is formed is drawn off the furnace and solidified. The purity of metallurgic silicon is around 98 up to 99%. 70% of the worldwide produced metallurgical silicon is used in the aluminum casting industry to make aluminum silicon alloy parts which are used in the automotive engine blocks. The other 30% is being used to make a variety of chemical products like silicones. Only around 1% of the metallurgical silicon is used to make electronic grade silicon. The silicon material with the next level of purity is called polysilicon. In the next animation, you see how out of metallurgical silicon, rods of polysilicon are produced. The source material is powder of metallurgical silicon. The metallurgical silicon is then exposed in a reactor with hydrogen chloride at elevated temperatures in presence of a catalyst. The silicon reacts with the hydrogen chloride and starts to form trichlorosilane. This is a molecule that contains one silicon atom, 3 chlorine atoms and 1 hydrogen atom. The trichlorosilane gas is cooled and liquefied. Impurities with higher or lower boiling points are then removed using distillation. The purified trichlorosilane is evaporized again in a different reactor and mixed with hydrogen gas. Trichlorosilane reacts with the hot rods, which are at a high temperature of 850 up to 1050 degrees Celsius. The silicon atoms are deposited on the rod, whereas the chlorine and hydrogen atoms are desorbed from the surface of the rod back into the gas phase. As a result, a pure silicon material is grown, and this deposition method is called chemical vapor deposition. As the exhaust gas still contains chlorosilanes and hydrogen, these gases are recycled and used again. Chlorosilane is liquefied and distilled and reused. The hydrogen goes through a cleanup process and is recycled back into the reactor. In the animation we have seen a chemical vapor deposition furnace that leads to polysilicon rods. This is the so-called Siemens process and consumes a lot of energy. Another method is the production of polysilicon granules in the so-called fluid bed reactors. This process operates at lower temperatures and consumes much less energy. Polycrystalline silicon can have an impurity as high as 99.9999%, or in other words, 1 out of 1 million atoms is not a silicon atom. Last, I would like to mention an alternative approach, that of upgraded metallurgical silicon. In this process, metallurgical silicon is chemically refined by blowing gases through the silicon melt, removing the impurities. Although this processing is cheap, the purity of its silicon is not as high as the Siemens or the fluid bed reactor approach. The next step is making wafers out of the polysilicon. But first, we consider 2 methods to make monocrystalline silicon ingots. Ingots are large blocks of crystalline silicon. The monocrystalline ingots are solids that consist of one big crystal. In the next animation, you will be introduced to the Czochralski processing method. Let's start with the Czochralski method, as developed by Polish scientist Jan Czochralski in 1918. It is a method to grow single crystal silicon. In this method, highly purified silicon is melted in a crucible at typical temperatures of 1500 degrees Celsius. Intentionally, boron or phosphorus can be added to make p-doped or n-doped silicon respectively. A seed crystal that is mounted on a rotating shaft is dipped into the molten silicon. The orientation of this seed crystal is well defined. It's either a 100 orientation or a 111 orientation. The melt solidifies at the seed crystal and adopts the orientation of the crystal. Crystal is rotating and pulled upwards, allowing the formation of a large single crystal cylindrical column from the melt. This big single crystalline silicon block is called an ingot. In this process, the temperature gradients, rate of pulling up and speed of rotations are precisely controlled. This process is further developed through years of advances, and nowadays crystal ingots of diameters of 200 mm and 300 mm with lengths of 2 meters can be processed. To prevent the incorporation of impurities, this process takes place in an inert atmosphere, like argon gas. The crucible is made from quartz, which partly dissolves in the melt as well. Consequently, Czochralski monocrystalline silicon has a relatively high oxygen level. The second method to make monocrystalline silicon is the so-called float zone process. This is a process which results in monocrystalline silicon ingots with extreme low densities of impurities like oxygen and carbon. The process is shown in the next animation. The source material is a polycrystalline rod as processed in the earlier mentioned Siemens process. The end of the rod is heated up and melted using a radiofrequent heating coil. The melted part is put in contact with seed crystals. Here it solidifies again and adopts the orientation of the seed crystal. Again, both 100 and 111 orientations are being used. As the molten zone is moved along the polysilicon rod, the single crystal ingot is growing as well. Many impurities remain in and move along with the molten zone. During the process nowadays, intentionally nitrogen is added, which improves the control on micro defects and improves the mechanical strength of the wafers. The advantage of float zone technique is that the molten silicon is not in contact with other materials like quartz, as in the Czochralski method. In the float zone process, the molten silicon is only in contact with the inert gas like argon. The silicon can be doped by adding doping gases like diborane and phosphine to the inert gas to get p-doped and n-doped silicon respectively. The diameter of float zone ingot is generally not larger than 150 mm, as the size is limited by the surface tensions during the growth. Next to monocrystalline silicon ingots, multicrystalline silicon ingots can be processed as well, as you can see in the next animation. Multicrystalline and polycrystalline silicon consist of many small crystalline grains. This can be made by melting highly purified silicon in a dedicated crucible and pouring the molten silicon in a cubic-shaped growth crucible. Here, the molten silicon solidifies into multicrystalline ingots. This process is called silicon casting. If the melting and the solidification occurs in the same crucible, it is referred to as directional solidification. The cross-section of a multicrystalline ingot can go up to 70 by 70 centimeters and the height is typically 25 centimeters. Now we know how to produce monocrystalline and multicrystalline ingots. How do we make wafers out of them? The answer is sawing, as you can see in the next animation. A disadvantage of the sawing step is that we waste a significant fraction of the silicon as a kerf loss. The kerf loss is usually determined by the thickness of the wire or saw used for sawing and is in the order of 100 microns of silicon. This is a large fraction of the ingot if we consider that typical crystalline silicon wafers used in solar cell nowadays are in the order of 150 up to 200 microns. Sawing will logically damage the surface of the wafers, so this processing step is followed by a polishing step. Silicon ribbon is a completely different approach to make wafers, as you will see in the next animation. Silicon ribbon does not face the problem of kerf losses, due to the simple reason that it does not include a sawing step. Silicon ribbon is the last processing method I would like to discuss. Silicon ribbon is based on a high temperature resistant string which is pulled up from a silicon melt. The silicon solidifies on the string and a sheet of crystalline silicon is pulled out of the melt like this. The ribbon is then cut into wafers. The surface is further treated before they are further processed into solar cells. The electronic quality of ribbon silicon is not as good as that of monocrystalline silicon. Summarized, we have discussed how out of quartzite we first make metallurgical silicon and then polysilicon. Monocrystalline ingots are made using either the Czochralski or the float zone process. Multicrystalline ingots are made using a casting method. Wafers are being made by sawing these ingots. A method which does not have any curve losses is the so-called ribbon silicon approach. Now we know how we make the wafers. Let's make solar cells out of them. We will discuss the design rules in the next block. Let's discuss the operating principle of the crystalline silicon solar cell. In this block, we will discuss several technical aspects which play an important role in the collection of the light-excited charge carriers and the reduction of the optical losses. Let's look at the solar cell. In week 2, we have discussed how an illuminated p-n junction can operate as a solar cell. In the illustration we have used in week 2, both the p and n doped regions have the same thickness. If you look at the crystalline silicon technology, this is not the case in real devices. Let's look at the most conventional crystalline silicon solar cell. The solar cell is based on a p-type silicon wafer. The n layer, in this illustration colored yellow, is the n-doped layer in the crystalline silicon PV technology. This layer is often called the emitter layer. This n-type emitter layer is much thinner than the wafer. The emitter has a thickness in the order of 1 micron. The rest p-doped wafer can be in the order of 100 up to 300 microns. As is discussed in week 3, a large fraction of light is absorbed close to the front surface of the solar cell. This is the generation profile as we have discussed in week 3. You see that in the first 10 microns, most charge carriers are excited. By making the front emitter layer very thin, a large fraction of the light-excited charge carriers generated by the incoming light are created within the diffusion length of the p-n junction. One of the processing methods to make the emitter layer is by solid-state diffusion. The wafers are placed in a furnace where the dopant atoms are present in atmosphere in the form of phosphine. These atoms react at these high temperatures with the surface. At these high temperatures, the dopant atoms are mobile in the solid, and based on Fick's law, the dopant atoms will diffuse into the wafer. Similar as we have discussed in week 2 for charge carrier diffusion, net diffusion occurs when there is a density gradient. The diffusion process is controlled such that the dopants penetrate into the solid to establish the desired emitter thickness. Now we are going to look at how the charge carriers in crystalline silicon solar cells are collected. We will discuss the crucial issues which play an important role in this charge collection. This includes the emitter layer, the metal contacts, and the back contact. Let's start with the emitter layer. At the p-n junction, the light-excited minority charge carriers are separated at the p-n junction. The minority electrons in the p layer drift to the n layer. These electrons have to be collected. Since the silicon N emitter is not conductive enough, we have to use the more conductive metal contacts. The metal contacts are placed on top of the emitter layer. Here the metal contacts are made of the cheap metal aluminum. This means that the electrons have to diffuse laterally through the emitter layer to the contact to be collected. Let's see what are the challenges for this transport of electrons to the contacts. First, last week we have discussed the importance of the high lifetimes of charge carriers. High lifetime guarantees large open circuit voltages, or in other words, the best utilization of the bandgap energy. This means that we have to reduce the recombination losses as much as possible. In addition, recombination limits the collected current as well. Recombination in silicon occurs, as discussed earlier, through Shockley-Reed Hall recombination and Auger recombination. Let's consider Shockley-Reed Hall recombination. A bare crystalline silicon surface contains many defects. The surface silicon atoms have some valence electrons which cannot make a molecular orbital with the absent neighboring atoms. These valence orbitals containing only one electron at the surface act like defects, also called dangling bonds. At these defects, the charge carriers can recombine through the Shockley-Reed Hall process. The probability and speed at which charge carriers can recombine is usually expressed in terms of the surface recombination velocity. Since a large fraction of the charge carriers are generated close to the front surface, a high surface recombination velocity at the emitter front surface will lead to charge carriers losses and consequently lower short circuit current densities as well. For example, high quality monocrystalline silicon wafers have no defect-rich grain boundaries in the bulk. The lifetime of the charge carriers is limited by the recombination processes at the wafer surface. In order to reduce the surface recombination, two approaches are used. The first is based on reducing the number of defects at the surface. This can be achieved by the deposition of a thin layer of different materials on top of the surface. This material partially restores the bonding environment of the silicon atoms. In addition, the material must be an insulator. It must force the electrons to remain in and move through the emitter layer. Typical chemical passivation layers being used on emitter layers are silicon oxide and silicon nitride. Silicon oxide layers are formed by heating up the silicon surface in an oxygen-rich atmosphere. The surface oxidizes, resulting in a thin layer of silicon oxide. Silicon nitride can be deposited using plasma-enhanced chemical vapor depositions. We come back to that process technology when we talk about thin film PV technologies. A second approach to reduce the surface recombination velocity is to reduce the minority charge carrier density near the surface. As the surface recombination velocity is limited by the minority charge carriers, a low as possible minority charge carrier density at the surface region would be beneficial. It means that with increasing the doping of the emitter layer, we decrease the density of the minority charge carriers. This results in a lower recombination velocity at the surface. However, this is again in competition with the diffusion length of the minority charge carriers. In this case, the hole is indicated by the blue dot. Note that many charge carriers are generated by the bluish photons close to the surface. To utilize these light-excited minority charge carriers, the diffusion length of the holes has to be large enough to reach the depletion zone at the PN junctions as indicated by the blue arrow. Increasing doping levels decreases the diffusion length of the minority holes in the emitter layer. Here you see an example in which the diffusion length has become so small that the minority charge carriers are unable to reach the p-n junction. Therefore, too high doping levels or too thick emitter layers would result in a poor blue response, or in other words, low EQE values in the blue part of the solar spectrum. Such layer could be referred to as a dead layer, as the light-excited minority charge carriers cannot be collected. Now we look in more detail to the metal-emitter interface. A problem at this metal-emitter interface is that we cannot use an insulating passivation layer like silicon oxide or silicon nitride anymore, as we need electrons to conduct from the semiconductor to the metal. This means that the metal semiconductor interface has more defects and therefore an unwelcome high interface recombination velocity. In addition, a metal semiconductor material induces a barrier for the majority charge carriers. In view of the scope of this course, it's too much detail to discuss this barrier in great detail. Keep in mind that this high barrier will give rise to a higher contact resistance. Again, high doping levels can reduce the recombination velocity at the metal semiconductor interface and reduce the contact resistance. As a consequence, it is preferred to reduce the area of the interface between the metal and the semiconductor to minimize the recombination at the interface defects as much as possible, and to have the emitter directly under the contact as heavily as doped as possible. This higher doped region is indicated by N++. In the figure, you see that the contact area between the metal and interface is kept as small as possible. The sides of the metal contacts are buried in the insulating passivation layer. The area below the contact has been heavily doped. These two approaches reduces the recombination and collection losses at the metal contact. The classical metal grid pattern on top of a solar cell looks like this. It's the roadmap for the electrons. Indicated in red, we see the highway for the electrons in the middle of the top surface of the solar cell. These are called the bus bars. The smaller country roads going from the bus bar to the edge of the solar cell are called fingers. First, the fingers have a resistance R. If L is the length of the finger, W the width of the finger, and H is the height of the finger, and rho is the electrical resistivity of the metal, we can describe the resistance R as rho times the length divided by the height and the width. The equation shows that the longer the path length for an electron will be, the larger the resistance the electron experiences. In addition, the smaller the cross-section, width times height, of the finger, the larger the resistance will be. Note that the resistance of the contacts will act as a series resistance in the equivalent electric circuit. Larger series resistance will result in lower fill factors of the solar cell as discussed in week 3. This means that you would like to have the finger cross-sections as large as possible. In this figure, we see that the electrons in the emitter have to travel in the lateral direction to arrive at the contact. Since the N-type silicon has a higher resistivity as the metal, the charge carriers in the metal layer also experience a resistance. In one of the exercises in this week, it is demonstrated that the power loss due to the resistivity of the emitter layer scales with the finger spacing to the power 3. As the metal contacts are at the front surface, they act as an unwelcome shading object, or in other words, light incident on the front contact area cannot be absorbed in the PV active layers. So you would like to keep the contact areas as small as possible, which is in competition with the fact that you would like to have a large as possible cross-section. So basically you would like to have as small as possible width and a high as possible height to comply with these requirements as demonstrated by the left contact. As you see, we have several effects which are in competition. Let's look for a moment at the relation between losses and the finger spacing. With increasing finger spacing, the power losses of the solar cell decreases due to shading. In contrast, the losses due to resistivity in the emitter layer and the metal fingers increases. This means that the total loss has a minimum. Similar plots can be made for the width of the contact. The larger the width, the larger the losses due to shading. The resistive losses in the metal fingers decrease with increasing finger width. Again, there exists a width which has a minimum loss. Optimizing the front contact pattern is therefore a complex interplay between the finger width and spacing. At the back surface of the solar cell, we have similar issues playing a role. As the electrons have to be collected in the n-type layer, the holes are collected at the back contact. As electrons are the only charge carriers that exist in a metal, you have to realize that the holes recombine with the electrons at the contact interface. If the distance between the PN interface and the back contact is smaller than the typical diffusion length of the minority electrons, the latter mentioned minority electrons can be lost at the defects at the back contact interface due to the Shockley-Reed-Hole recombination. How can we reduce this loss mechanism? First, we can reduce again the area between the metal contact and the semiconductor. We can make point contacts. The rest of the rear surface is then passivated by an insulating passivation layer, similar as we have discussed for the cases of the emitter front surface. The loss mechanism of recombination of electrons at the back contact can be further reduced by a so-called back surface field. A higher p-doped region is placed above the point contacts at the rear surface, indicated by P++. How does the back surface field work? For the moment we have put the solar cell on its side. Below the solar cell you see the Venn diagram indicating the various interfaces. The interface between the lower doped P region and the higher doped P region acts like a PN junction. In this case, it will act as a barrier for the light-excited minority electrons in the lower doped region to diffuse to the back surface. The space-charged field behaves like a passivation of the defects at the back contact interface and allows to have higher levels for the electron minority density in the p-doped bulk. Up to now we have talked about managing the charge carriers. Now we are going to discuss the management of the photons in a crystalline silicon solar cell device. The optical loss mechanisms are shading, reflection losses, parasitic absorption losses in the non-PV active layers, a light that is not absorbed in the silicon layers and is lost at the back contact. Shading losses are caused by the front contact grid as discussed earlier. The optimum contact grid at the front is a competition between reduction of the shading losses and a reduction of the resistivity losses in the metal contact and the emitter layer. Secondly, the reflection at the front surface can be considered as a loss mechanism. Last week we have discussed two approaches to reduce the losses. The first one was based on the Rayleigh film principle. By putting a film with a refractive index smaller than that of the silicon wafer between air and the wafer, you can reduce the losses. The optimum value for the refractive index of the intermediate layer equals square root of the product of the refractive indexes of the two other media. For silicon and air at 500 nanometers, this leads to an optimum refractive index of 2.1. Note that in practice a solar cell is encapsulated under a glass plate. The glass plate will be beneficial to refractive index grading as well, reducing the reflection losses further. Secondly, using the concept of destructive interference, we can choose the thickness and refractive index of an anti-reflection coating such that in a certain wavelength the irradiance coupled out of the solar cell is minimized. The light reflected from the front surface is in antiphase with the light reflected from the back surface, as discussed last week. The thickness of such layers should be the wavelength divided by 4 times the refractive index. If we take a welcome reflective index of 2.1, we arrive for light of 500 nanometers at an optimal thickness of 60 nanometers for an anti-reflection based on destructive interference. As we have discussed earlier, one of the typical passivation layers of standard crystalline silicon is silicon nitride. Here we see a multicrystalline silicon wafer without silicon nitride layer. We see that a lot of light is reflected by the wafer. Next to it, we see a multicrystalline silicon with a silicon nitride passivation layer. As you can see, much less light is being reflected. Interestingly, the refractive index of silicon nitride is in the range of 2 up to 2.2 at 500 nanometers, close to the optimum for the refractive index grading. Typical thicknesses are in the same range as the 60 nanometers discussed earlier. Note that the surface of the solar cell looks a bit bluish. This shows that the reflection of blue light by the silicon nitride is larger than for the other wavelengths. As discussed last week, texturing of the surface can improve the light in coupling as well. Light that is reflected at the textured surface can be reflected at angles in which the trajectory of the light ray is incident somewhere else on the surface. Here the light can be still coupled into the silicon. Secondly, the scattering at textured surfaces will couple the light under angles into the wafer. This means that the absorption path length will be enhanced. This certainly enhances the welcome absorption of the light with a wavelength above 900 nanometers. The texture on the wafers can be realized with wet etching approaches. Here you can use an interesting property of the 100 surface. This anisotropic etching can be used when etching a crystalline silicon wafer with an initial 100 surface orientation. Etching of such wafer leads to the textured surfaces with a pyramid structure having only 111 oriented surfaces. In this picture you can see such textured surface of a monocrystalline silicon wafer as processed at the Demus lab in Delft. Using such etching procedures, it's even possible to have a silicon wafer looking black as shown here in the second picture. Here we see a flat multicrystalline silicon layer with and without silicon nitride. Under these wafers we see 2 wafers with and without silicon nitride layers as well. The only difference is that the 2 wafers at the bottom have textured surfaces. The wafers are placed in the same illumination conditions as the flat wafers. By eye you can already see that these surfaces are darker and therefore reflect less light. So we have discussed the general design rules for crystalline silicon solar cells. In the next block I will show you 3 different concepts of high efficiency crystalline silicon solar cells. As you will see, they are based on the design rules we have discussed in this block. See you in the next block. In the previous block, we have discussed various technological aspects on crystalline silicon wafer-based PV technology. In this block, I will give you 3 examples of highly efficient solar cells based on crystalline silicon wafers. As discussed earlier this week, we have various types of wafers with different qualities of silicon. To achieve the highest efficiencies, the bulk recombination must be as low as possible. Therefore, the high efficiency crystalline silicon solar cells are based on monocrystalline wafers. Let's start with the first high efficiency crystalline silicon solar cell developed by Martin Green's group at the University of New South Wales in the late 80s and the early 90s. Here you see an illustration of the Pearl concept, which uses a p-type float zone silicon wafer. This concept has approached a conversion efficiency of 25% and has been an example for various technologies developed afterwards. Pearl is an abbreviation for passivated emitter rear locally diffused. The name indicates the two important concepts integrated into the solar cell. The optical losses of the Pearl solar cell at the front side are minimized using three important concepts. First, the top surface of the solar cell is textured using inverted pyramid structures. This microscopic texture allows a fraction of the reflective light to be incident on the front surface for a second time. This enhances the total amount of light coupled into the solar cell. Secondly, the inverted pyramid structures are covered by a double layer anti-reflection coating, which results in an extremely low top surface reflection. Often, a double layer coating of magnesium fluoride and zinc sulfide is used as an anti-reflection coating. Thirdly, the contact area at the front side has to be as small as possible to reduce the shading losses. In the Pearl concept, these very thin and fine metal fingers are processed using photolithography technology. The emitter layer is smartly designed. As discussed in the previous blocks, the emitter should be highly doped underneath the contacts, which in the Pearl concept is achieved by heavily phosphorus diffused regions. The rest of the emitter is moderately doped, or in other words, lightly diffused, to preserve an excellent blue response. The emitter is passivated with a silicon oxide layer on top of the emitter to suppress the surface recombination velocity as much as possible. The surface recombination velocity has been suppressed to the level that the open circuit voltages with values of above 700 millivolts have been obtained using the Pearl concept. At the rear surface of the solar cell, point contacts have been used in combination with thermal oxide passivation layers. The oxide operates as a passivation layer of the non-contacted area to reduce the unwelcome surface recombination. A highly doped boron region created by local boron diffusion operates as a local back surface field to limit the recombination of the minority electrons at the metal contact. The Pearl concept, as we presented here, includes some expensive processing steps. The Chinese Suntech company developed in collaboration with the University of New South Wales a more commercially viable crystalline silicon wafer technology which is inspired on the Pearl cell configuration. A second successful cell concept, which is commercialized by SunPower, is the interdigitated back contact solar cell. The principle of interdigitated back contacts concepts is that it does not suffer from shading losses of a front metal contact grid. All contacts responsible for collecting of charge carriers at the N and P side are positioned at the back of the crystalline wafer solar cell. An advantage of these interdigitated concepts are that you are able to use monocrystalline float zone N-type wafers. Why is that interesting? The N-type wafers have some advantages above P-type wafers. First, the N-type wafers do not suffer from light-induced degradation. In P-type wafers, simultaneously boron and oxygen are present, which under light exposure start to make complexes that act like defects. The light-induced degradation causes a reduction of the power output with 2 to 3% after the first week of installation. This effect is not present in N-type wafers. The second advantage is that N-type silicon is not that sensitive for impurities like, for instance, iron impurities. As a result, less efforts have to be made to make a high electronic quality of N-type silicon, meaning that high quality N-type silicon can be processed cheaper than P-type. On the other hand, P-doped wafers have the advantage that the boron doping is more homogeneously distributed over the wafer as for N-type. This means that within one N-type wafer, the electrical properties can vary within the same wafer. This effect lowers again the yield of a solar cell production based on N-type monocrystalline wafers. Back-contacted solar cells use, in contrast to the pearl concept, N-type float zone monocrystalline silicon wafers. An interdigitated back contact is lacking one large p-n junction. Instead, the cell has many localized junctions. The holes are separated at a junction of P+ and the N-type silicon, whereas the electrons are collected using an N+ type silicon. The semiconductor metal interface is kept as small as possible to reduce the unwelcome recombination at this defect-rich interface. Another advantage is that the cross-section of the metal fingers can be made much larger to reduce the resistive losses of the contacts as much as possible. The fact that the contacts do not cause any shading losses at the back allows them to become larger. The passivation layer can have a low refractive index such that it operates like a backside mirror. It will reflect the light above 900 nanometers, which is not absorbed during the first pass, back into the absorber layer, enhancing the absorption path length. An interdigitated back contact solar cell would look like this. At the back, you have two metal grids. One collects the current of the N-type contacts, and the other collects the current of the P-type contacts. At the front side, the losses of the light-excited charge carriers due to surface recombination is suppressed by using the same tricks like the back surface field as discussed for the rear surface for solar cells based on P-type wafers. The surface recombination velocity of the front surface is determined by the minority charge carriers, in this case the electrons. At the front side, the losses of the light-excited charge carriers due to the surface recombination is suppressed by using the same tricks like the back surface field as discussed for the rear surface for solar cells based on P-type wafers. The surface recombination velocity of the front surface is determined by the minority charge carriers, in this case the holes. Consequently, we have to create a front surface field. A higher N-doped region is placed at the front surface indicated by N+. The interface between the higher doped N region and the lower doped N region acts again like a p-n junction. In this case, it will act as a barrier for the light-excited minority holes in the lower doped region to diffuse to the front surface. The front surface field behaves like a passivation of the defects at the front interface and allows to have higher levels for the hole minority densities in the p-doped bulk. At the front side, the reflective losses can be reduced using the same tricks as discussed for the pulse solar cell. Deposition of double-layered anti-reflection coatings and texturing of the front surfaces. SunPower is the company that has developed a cell technology based on interdigitated back contacts. And they have achieved high solar cell efficiencies of 24.2%. An alternative concept with high efficiency is the so-called crystalline wafer-based heterojunction solar cells, as you see in this illustration. First, I have to answer the question, what is a heterojunction? So far, I have introduced you to the concept of p-n junctions with a depletion zone. These junctions are fabricated by different doping types within the same semiconductor material. This means the band gap in the PN doped material is the same. Such PN junction is called a homojunction. However, you can also make a junction by two different semiconductor materials. For instance, one semiconductor material that is p-doped and another type of semiconductor material that is n-doped. This is what we call a heterojunction. In the crystalline silicon wafer-based heterojunction, we make use of two types of silicon-based semiconductor materials. One is again an N-type float zone monocrystalline silicon wafer. The other material is hydrogenated amorphous silicon. This is a silicon material in which the atoms are not ordered in a crystalline lattice, but in a disordered lattice. Next week, I will come back to this material when we are discussing thin film technologies. For the moment, you only have to know that this material has a higher band gap than that of crystalline silicon. Secondly, amorphous silicon can be N-doped and P-doped as well using phosphorus or boron. I won't go in detail, that is out of the scope of this course, but the electronic band diagram of a heterojunction of N-doped crystalline silicon and P-doped amorphous silicon in the dark and thermal equilibrium will look like this. You see that next to the induced field due to the space charge region, some local energy steps are introduced. These steps are caused by the fact that both band gaps are not the same. At this junction, you see that the valence band is higher positioned in the p-type amorphous silicon in reference to the n-type crystalline silicon. This will allow the minority charge carriers, the holes, to drift to the p-type silicon. However, you see in this example that the holes experience a smaller barrier. In contrast to classical mechanics, a particle cannot move through such barrier. In the case of quantum mechanics, this is still the case. A large fraction of the holes can move through this barrier, and this phenomena is called tunneling. Now let's go to the crystalline silicon wafer-based heterojunction solar cell. This is a concept which has been invented by the Japanese company Sanyo, which is currently part of Panasonic. The Panasonic cell is called the HIT cell, which stands for heterostructure with intrinsic thin film. The HIT cell configuration has two junctions. The junction at the front side is formed using a thin layer of only 5 nanometers of intrinsic amorphous silicon, which is indicated by the red color. A thin layer of p-doped amorphous silicon is deposited on top, and here is indicated with the blue color. The heterojunction forces the holes to drift to the p layer. At the rear surface, a similar junction is made. First, a thin layer of intrinsic amorphous silicon is deposited on the wafer surface, indicated by the red. On top of the intrinsic layer, an N-doped amorphous silicon is deposited, indicated by the yellow color. As discussed earlier, for high-quality wafers like this N-type float zone monocrystalline silicon wafer, the recombination of charge carriers at the surface determines the lifetime of the charge carriers. The advantage of the HIT concept is that the amorphous silicon acts like a very good passivation material. In this approach, the highest possible lifetimes for charge carriers are accomplished. The crystalline silicon wafer-based heterojunction solar cell has the highest achieved open circuit voltages among the crystalline silicon technology. Panasonic achieved an open circuit voltage of 750 millivolts. How do the charge carriers travel to the contact? The conductive properties of the p-doped amorphous silicon are relatively poor. In the homojunction solar cells, the diffusion to the contacts takes place in the emitter layer. In contrast, in a HIT solar cell, this occurs through the transparent conductive oxide material, like an ITO, which is deposited on top of the p-doped layer. The ITO is needed as the conductivity of the p-type layer is too poor. This results in such small diffusion lengths that a practical metal fingal spacing cannot be achieved using the p-type layers. Therefore, ITO is used. An advantage of the HIT cell concept is that it allows to introduce the same contact scheme at the n-type backside. It means that this solar cell can be used in a bifacial configuration. It can collect light from the front and scattered and diffuse light falling on the backside of the solar cell. Another important advantage of the HIT solar cell is that the amorphous silicon layers are deposited using cheap and straightforward plasma-enhanced chemical vapor deposition technology at low temperatures, not higher than 200 degrees Celsius. This means that making the front surface and the back surface field in this type of solar cells is very cheap. Furthermore, this technology allows to use the N-type wafers. Summarized, the high-efficiency crystalline silicon wafer-based solar cells are shown here. The record efficiency of a Pearl solar cell was 25%. However, this was a lab-scale solar cell with an area of 4 square centimeters. The record efficiency for an interdigitated crystalline silicon solar cell has been achieved by SunPower. They achieved an efficiency of 24.2% on a wafer size of 155 square centimeters. Finally, for the crystalline silicon-based heterojunction solar cell, Panasonic achieved an efficiency of 24.7% on a wafer size of 102 square centimeters. The efficiency for multicrystalline silicon solar cells are lower as the wafer quality is lower. The best efficiency achieved is 19.5 by Q cells on a wafer with a size of 243 square centimeters. This is around 5% absolute below the record efficiencies based on monocrystalline silicon wafers. Now, we know the efficiencies of solar cells. However, in practice, we install panels on our roof. In the next block, we will answer the question, how do we make solar modules out of solar cells? We now know what a solar cell is, but how do we make a module out of solar cells? What is the performance of a solar module? These are questions I will answer in this final block. A wafer-based device is usually referred to as a solar cell. A solar module is a large device in which many solar cells are connected. If you look at the level of a PV system, we can have several modules connected, and this is what we call an array. Now we look at how we make a solar module out of an ensemble of solar cells. We can connect the solar cells in different ways. First, we have the series connection, as shown in this figure. In a series connection, the voltages add up. It means that if the open circuit voltage of one cell is equal to 0.6 volt, the string of the 3 cells deliver an open circuit voltage of 1.8 volt. If you look at the classical front metal grid, it means that the bus bars at the front side have to be connected with the back contact of the neighboring cell. In this slide, you see a cross-sectional view of a few solar cells connected in series. Every solar cell has its back contact connected with the front contact of its neighboring cell. For series connected cells, the current does not add up. The current flowing through the solar cell is determined by the photocurrent in each solar cell. It means that the total current in the string of solar cells is equal to the current generated by one single solar cell. Let's look at the JV curve of solar cells connected in series. If we connect 2 solar cells in series, it means that we can add up the voltages. However, the current remains the same in series connection. The resulting open circuit voltage is 2 times that of the single cell. If we connect 3 solar cells in series, the open circuit voltage becomes 3 times as large, whereas the current is that of one single solar cell. A second way of connecting the solar cell is in parallel. Here you see 3 solar cells connected in parallel. The IV curve shown is that of a single solar cell. Parallel connection means that the voltage is the same over all solar cells. However, the currents of the solar cells add up. If we have 2 solar cells connected in parallel, the current increases 2 times, whereas the voltage remains the same. If we have 3 cells in parallel, the current becomes 3 times as large, while the voltage is the same as for a single cell. This means that if we consider a module, you can partly tune the voltage and the current output by the arrangements of the connections of the solar cells. Here we see a typical solar panel that contains 36 solar cells connected in series. If a single junction solar cell would have a short circuit current of 5 amperes and an open circuit voltage of 0.6 volt, it means that the current output of the module is equal to that of a single solar cell, which is 5 amperes. The open circuit voltage would be 36 times that of a single junction cell, which equals to 21.6 volts. If we would rearrange the connection of this module, we can get a different current and voltage output. If we connect 2 strings of 18 series connected solar cells in parallel, we would get a short circuit current density of 2 times that of a single solar cell, which is 10 amperes. The open circuit voltage would be 18 times that of a single solar cell, which is 10.8 volts. Another aspect of modules is that some bypass diodes are integrated into the modules. Why do we need bypass diodes? For that we have to look at a solar module in real life. In real life, the solar module can be partly shaded. This can be the shade of an object nearby, like a tree, a chimney, or a neighboring building. The shading can be caused by a simple leaf that has fallen from the tree. This can have significant consequences for the output of the solar module. Let's consider the situation in which one solar cell in the module is for a large part shaded. For simplicity, we assume that all 6 cells, part of this small module, are connected in series. This means that the current generated in the shaded cell is significantly reduced. In a series connection, the current is limited by the cell producing the lowest current. This cell dictates the maximum current flowing through the module. In this JV curve, we show the theoretical JV curve of the 5 non-shaded solar cells and the 1 shaded solar cell. If we have a constant load like the resistance R in the previous picture, it means that the voltage over the module is dropping due to the lower current generated. However, since the 5 no-shaded solar cells are forced to produce high voltages, they act like a reverse bias source on the shaded solar cell. The dashed line represents the reverse bias load put on the shaded cell. It is the JV curve of the 5 cells mirrored into the vertical axis equal to 0 volt. This means that the shaded solar cell does not generate energy but starts to dissipate energy. It means the solar cell is getting warmer and warmer. The temperature can increase to such a critical level that the encapsulation material cracks or other materials wear out. In general, high temperature conditions lead to a decrease of PV output as well. This can be prevented by including bypass diodes in the module. In this figure you can see bypass diodes included in the electric circuit. A diode, as discussed in week 2 and 3, blocks the current in a direction when it's under negative voltage, but conducts a current when it's under positive voltage. If no cell is shaded, no current is flowing through the bypass diodes. In the case that one cell is shaded, Due to the biasing of the other cells, the bypass diode starts to pass current through. As a result, the current can go around the shaded cell and the module can still produce the current equal to that of a non-shaded single solar cell. As you can see, going from a solar cell up to module level gives rise to a whole new set of technical considerations. In week 7, we will discuss the operation of modules and their design considerations in the PV system in greater detail. So this week, we have discussed crystalline silicon wafer-based PV technology. I hope it was a helpful introduction into this technology. You have to realize that in view of time limits, we only covered the most rudimentary concepts. In the next week, we will discuss different PV technologies. Technologies which are based on thin film materials, such as amorphous and nanocrystalline silicon, cadmium telluride, CIGS, dye-sensitized and organic materials, and the 3-5 semiconductor materials. You will discover that every technology will have its own specific design rules and challenges. See you next week.